We started this week's lecture building on the previous week's introduction to finite volume method. We further developed the ideas of perfectly matched layer technique introduced in the earlier lectures for advanced applications. We looked into a simplified uniaxial perfectly matched layer formulation for finite volume time domain simulation. We showed some applications using rectangular geometry using this PML formulation. We further extended this idea to include a more general radial uniaxial PML, showcasing both the pros and cons of this generalized formulation for 2D applications. We later studied using a simple waveguide problem the efficacy of radial uniaxial PML for finite volume time domain applications. We also compared the performances of the standard Silver-Muller absorbing boundary condition and uniaxial radial PML in the finite volume framework. We demonstrated the impact of source locations in the PML absorption behavior. Later, we discussed the critical role the radius of curvature of radial PML plays in the PML absorption performance. We later discussed some practical tips for making some trade-off between accuracy and computational costs while using these advanced methods. We also simulated some advanced applications like horn antenna and coupling between two Archimedean spiral antennas using radial PML and Silver-Muller absorbing boundary condition in the finite volume framework. We compared the computed radiation pattern and cross-coupling to discuss the performance of different domain truncation techniques in the finite volume time domain method. Finally, we also discussed one of the biggest challenges while using finite different time domain method, namely the numerical dissipation. We also discussed the source of such dissipation while computing the flux function and how it is inherently tied to the manner in which we do the spatial discretization and compute the flux function. We also briefly alluded how and why co-locating electric and magnetic fields in space and time affect the duality relationships that exist between them. We mentioned the collocation in space and time while using the finite volume formulation doesn't consider the underlying topological aspect of the electromagnetic quantities. Towards the end, we also introduced a simple heat conduction problem using finite volume method and also explained how we can model such problems using MATLAB. In this week's lecture, during the lab tour, we also modeled and simulated a permanent bar magnet and monopole antenna problems. Carefully learn the theoretical aspects and applications we studied this week. Finite volume time domain method is not normally discussed in any graduate coursework in computational electromagnetics. Hence, take this opportunity to learn as much as you can during the coursework and also discuss your doubts in the forum. In the next week, we will be introducing one of the most beautiful methods in computational electromagnetics based on algebraic topology. This is one of the rarest methods that you will learn in any coursework on computational electromagnetics. I'm very much excited and I hope you are equally excited as well. So we will see you next week. Until then, goodbye.